Now let's use some very simple mathematics to try understand what's this idea of finite element analysis by discretizing a continuous piece of object into individual components and put it back together. Now the simplest example we can think about is what happens if you do differentiation to a continuous piece of function. Now you know what continuous function mean in mathematics. Basically that means if you have a function and you can draw that curve without leaving your pen out from the paper, then that piece of function is continuous. Now what can you do to a continuous function? Well, we can differentiate it. As you show here, we have a very simple function called x squared, and you know that x squared is a parabola, is continuous everywhere on the x-axis. And we know how to differentiate this simple polynomial x squared, which is basically 2x, right? And if you want to know the derivative at x equal to 1, you basically plug in x equal to 1 to 2x. That gives you a value of 2, right? That's very simple. But in many computational problems, it's not so common that you can actually differentiate with respect to a no analytical form. Many problems we deal with, we don't know the analytical derivative of the function. We only know what's the value of the function fx at a certain point x. Now, how do we do that? Basically, we need to go back to the original definition of derivative and do it in a discretized manner. So what's the definition of derivative? Well, if you go back to your first year calculus, you know that the derivative is basically the change in the functional value with respect to the change in the independent value. So it's the ratio between the two. If you write that down, for example, at a given x, I can always increment x by a small number delta. Now I can then calculate the functional value at x plus delta and x, and I divide the difference by the increment in x, in this case, which is basically delta, and I evaluate this whole expression at x equal to 1. Of course, this function or this expression only gives the derivative at x equal to 1 if you take the limit of delta goes to 0. But in most of the cases, you might not be able to do that. So what you do is basically give a very, very small value of delta and try to evaluate this expression behind. Now, what happens if you plug in x squared into this expression? Well, you can get 1 plus delta squared minus 1 squared, because when you evaluate at 1, so this is what happened at the top. And at the bottom you have delta, which is x plus delta minus x. That gives you delta squared plus 2 delta over delta. So if you expand the bracket, manipulate the expression a little bit, that gives you this one. And you can simplify this a little bit, knowing that delta is not 0. That gives you delta plus 2, okay? Now, in this case, we can take the limit delta goes to 0, that gives you 2, which is basically the derivative of x squared at 1, at x equal to 1. But if you don't know, or in many computer algorithms where you can't actually take the limit, what you basically do is give delta a very small number, as I said before. In this case, say you give a number of 10 to the minus 10, then delta plus 2 is 2 with dot 0.00001. So it's a very small a number very, very close to 2, and in that case you can say, okay, the derivative of this function is basically 2 at x equal to 1. So this is an example of going back from a continuous function to a discrete cases where you can sort of program into an algorithm and calculate it in the case where you don't really know the analytical form of your function, right? So if we look at the example so far, we see that the finite element analysis is a case where we want to analyze the mechanical property of structures, right? For some simple structure like trusses, beams, like horizontal, uniform metal bar, uniform wooden bar, everything is uniform, we know the shape. Those structures are with simple geometry, and we can use some simplification or idealization to work out what happens if some forces is applied to them. For example, we can assume that all the mass of the structure is concentrated at one point, as I used the example at the very beginning, right? If the mass distribution is uniform, right, in that case, the center of gravity or center of mass will coincide with the geometry center of a of the whole shape, right? For example, if you have a circular disk where the mass is uniform distributed, then the center of the gravity or center of mass will be at the center of the radius, right? And if you have like beams, then you can chop it up into individual beam segments, provided that they also have a uniform cross-sectional area. Now, if you can, simplify your object in such a way that you will be able to work out what's the loading if I apply a force to it, and then based on this idealized geometry, you can say, okay, the safety factor or the tolerance where this piece of structure can be applied in real mechanical loading scenario is probably like within some safety factor, like 1.5 to 3 times of the deformation I expected under given loading. So that's all fine if you have things that are simple. But the world is not always simplified in that case, so we need to take a lot of complicated factors into account, and this is what we'll be looking at in the subsequent section of the course.